I'm going to make a few comments about having worked with Ted Madden and Freeman Gilbert in the earliest of days in the frequency domain induced polarization, which was Ted's idea, as we all know, and which the SEG recognized him for, I think it was 1970 possibly, a long time after it was developed. I worked with Freeman Gilbert and Ted in 1956 doing induced polarization field studies. We were stationed in Baker, California. Any of you who know the road between Los Angeles, somebody's shaking their head up and down, they know it. There's a 5-mile Baker grade. We were down at the bottom in Baker. And it was challenging field work. You got to lay out lines, you got to pick them up. You got to lay them out, pick them up. I learned in that field work, one, you get up early for field work when you're working out in the desert. You get up at about 3:30 or 4 o'clock in the morning, and you take along with you these desert water bags that evaporate, cool, and you yourself are thermostatically controlled, so in a sense, you drink a lot of water and it evaporates. You don't use any other discharge method in the deserts. It was very challenging. We then also went on to southwestern Arizona, stationed in Safford, Arizona. Well, that was a great summer, and that was the first graduate year for me at MIT. Second summer, I worked with Ted. Again, we were working for Bear Creek Mining Company. That's what it was called back then, George Rogers. And we were helicopter supported doing induced polarization work literally above timberline up in the Cascade Mountains north of Bellingham, Washington, state of Washington. Beautiful place. You look out on Mount Baker. There were the Sierra mountaineers who came through and taught me one thing about people who go out camping and all of that. And that is, since there's both boys and girls, and you frequently camp down near a pond or a lake or something like that, there's geographical distribution. The boys on one side, the girls on the other side, and in between the married couples. At least at that time, there were married couples in between, so that there was no transfer of personnel. They thought we had life knocked because we got paid good money for being up there. Well, it was a bit of hard work lugging around at what at that time was portable IP hardware that I and a couple of other people had built. I followed induced polarization development. There was a fellow, Phil Haloff, who some of you will remember. We went up to Canada, and he passed away very early in life, most unfortunately. And at that time, Don Marshall and I were graduate students, and I think Bill Thompson's going to talk about that in his reflections during the memorial service. I'm going to talk about the space business that I got involved with early in the space age. My career has been with NASA. I'm very thankful for this particular federal agency demonstrating how, with a very well-defined objective, well-funded, and the right people working on it, it can be a real winner for everybody involved. It's been an extremely exciting time for me. If I can point here no, not yet. I think that the missions I'm going to talk about, Voyagers 1 and 2, that's what the title of this talk is supposed to have been. I'm going to really concentrate on Voyager 1. I think it can be classified as the robotic twin spacecraft mission of the 20th century for NASA because of all of the science that has come out and the broad fields it covers. For those of you not familiar with what it is, I'm only going to just touch on them just very, very lightly. I'm going to concentrate only on the newest results that we're obtaining. and show you the first in situ measurements of the interstellar magnetic field. That's outside the influence of our sun. Adolfo has given you a very nice introduction to how our active sun influences our environment and how complicated and challenging the analysis of collisionless magnetized plasma information data can be in order to understand the dynamics of structures, not only shocks, but there are what we call tangential discontinuities, rotational discontinuities, and of course all sorts of waves stimulated by instabilities depending upon the geometry of the magnetic field, et cetera, so on and so forth. Next slide, please. In the space business, it got very traditional that NASA would issue a solicitation for proposals to the scientific community. So that even though I was an employee of NASA or other people, we have to submit proposals and compete with Lockheed, Boeing, Martin, MIT, universities, not only from this country, but also NASA puts foreign provided instruments on board its spacecraft. There was a mission that I proposed for along with others, and I'll talk about some of their results and who they are shortly. In 1970 for what was called the Mariner Jupiter-Saturn. Now, why two spacecraft? Well, in the early days of the space business, the rockets were unreliable, really, often, and sometimes the spacecraft had trouble, but much less. But most often, it was the rockets in the first decade of the space business. In 1977, the two spacecraft were launched. It was known then, in 1970, actually, that that was the time to launch when you could use the gravity assist technique of close flybys of any of the planets to distort the spacecraft trajectory as sort of a mid-course maneuver and do it very effectively, which it was done with both Voyagers 1 and 2 launched in 77. Fortunately, the committee that had reviewed the proposals for NASA doing these missions strongly recommended that the spacecraft carry along a lot of additional propellant for reorienting and adequate power to make sure that it would be success just for Mariner, Jupiter, Saturn. Everybody had in their minds, not everybody, fortunately not the administrators who were approving the funding of this mission, or at least if they did, they didn't recognize it, didn't do anything about it. So the spacecraft got loaded up with plenty of power and plenty of extra propellant for mid-course corrections or reorientations, et cetera. And we began the grand tour of the giant planets. We went to all of those 4 planets in a time scale 79 to 89. Now, Voyager 1 was actually launched second, but it was the first spacecraft to reach Jupiter. Jet Propulsion Laboratory, which manages and operates the Deep Space Network, which tracks spacecraft in the planetary program for NASA, has a numbering system, and that's how they numbered it. That was going to be spacecraft 61, number 1, and that was it. We did twin flybys of Jupiter and Saturn with both of them, but only a single flyby of Uranus and Neptune with Voyager 2. Next slide, please. Where are Voyager 1 and Voyager 2 today? This is just to give you a perspective on the scale of this mission. This was back in the middle of 13. Well, that's pretty long time ago in a sense. Back then, Voyager 1 was 125 and Voyager 2 at 102. Voyager 1 was chosen and reoriented so that it would get out there the fastest. The power of these radioisotope thermoelectric generators, we've got power that will operate all of the meaningful instruments on board the spacecraft until the year 2020 with the antenna capabilities that currently exist. The instruments data that I'm going to be showing to discuss these first measurements of the interstellar magnetic field come from the cosmic ray science experiment of Dr. Edward Stone from Caltech, the low energy charged particle experiment from Dr. Stamidos, Tom Cremegis as he's known, from Johns Hopkins University Applied Physics Lab, and I'm the PI on the magnetometers. I joined NASA and got into the magnetometer business because I had a couple of friends who at that time were working in anti-submarine warfare for an electronics firm in California, Ken Ruddick and Earl Bloom. They were building rubidium vapor magnetometers. They didn't know what to do with the data. They wanted to see it advertised. They heard I was going back to NASA. I'd graduated from MIT, went to UCLA, and had an invitation to go back to the then very early NASA in 1959. Well, I went back in 1960, and they said I should hook up with somebody using rubidium vapor magnetometers on spacecraft. That was my invitation. Next, please. So, Voyagers 1 and 2 were launched. This is an overview. You've seen sort of a sketch of this, but this is now in more detail. Launched in '77, Voyagers 1 and 2. They went by Jupiter shortly after launch in '79. They then both went by Saturn, and then Voyager 2 continued on for Uranus, and Neptune was then with Voyager 2 also in 1989. That meant it only took from '77 to '89, 12 years. Not very long to get there. Incredible, actually, because with the rockets that we had available to us, it would have taken, with a direct ascent launch to Neptune, about 20 years to get there. And this gravity assist celestial gymnastics, as I call it, a technique that's been pioneered by people like Bob Farquhar. He's got a wonderful book about how he has used the gravity assist and the gravity of various planets and the moon in shaping trajectories. Next slide. After its Saturn flyby, Voyager was targeted to follow a trajectory to reach the outer heliosphere quickly. That's in a certain direction relative to the motion to the stars. We're moving through space, we think, at about 26 kilometers per second. That number has been changed recently by the astrophysicists, but that's sort of what we think, the local intergalactic space. I've mentioned item 2. Both spacecraft were reprogrammed to continue recording radio waves, an instrument on board with Dr. Don Gurnett from the University of Iowa, which measures the local plasma waves that are present. It was mentioned by Adolfo. And of course, plasma. As it turns out, the MIT-provided plasma experiment failed on Voyager 1 after the Neptune encounter for some reason unknown. No, it failed on Voyager 1 after the Saturn encounter, but it's working on Voyager 2, and it will probably encounter the boundaries that I'm going to discuss with you now as we leave the solar system region of space. And these radio waves that Don Gurnett is mentioning are these plasma waves which Adolfo had mentioned. And also the radiation which arrives at the spacecraft. Next. So this is a geometry. You've seen a sketch like this of the concept that we have. Here's the interstellar space. And between us, between that and the sun are these boundaries. This is the heliosphere. Then there is the termination shock. Then there's the heliopause, which is analogous to the magnetopause of the solar wind interaction with the planetary magnetospheres. And then there's this region of space not previously explored beyond the heliopause because we hadn't really identified the heliopause crossing until relatively recently. Next slide. This is data taken from the low energy charged particle experiment, and this is a time scale of 2004 to 2014. Low energy particle energies are identified here. At the end of 2004 is when we crossed what we call the termination shock region. It's identified in some of the magnetic field data I'll show a little bit better. What I want to point out here is these low energy particles just seem to drop out in this instrument's detection. Meanwhile, the higher energy cosmic ray particles seem to increase a little bit at the time they're dropping out. Next slide. If we look a little bit closer at how these particle variations change with the magnetic field here, this is now over a time scale of about 2/3 of a year. What we see is that the magnetic field drops down, comes back up, drops down, and there's some apparent boundaries in here in which the magnetic field is getting up to. This intensity is 0.4 nanotesla. If you don't know what a nanotesla is, maybe you know what a gamma is. In any event, it's a very weak magnetic field. To make these weak magnetic field measurements, we developed a technique called the dual magnetometer technique. We mount on a 13-meter boom on the Voyager spacecraft 2 triaxial magnetometers and compare the measurements and make the assumption that the coupling coefficient between the two of them is equivalent to a centered dipole for the spacecraft. The boom that is extendable was actually developed by a Canadian firm for elevating antennas in the Vietnam jungle during the Vietnam War because the jungle canopy completely shields radio waves. And this is a collapsible, it's sort of like one of those toys that jumps up. But this is 13 meters that it goes to, and it's non-magnetic. That's another challenge making magnetic field measurements of very weak magnetic fields. You've got the magnetic fields of the spacecraft to contend with. Well, that's how we tried to solve it with the booms and working with each of the individual instrumenters on board the spacecraft and the power system supplied. Well, we see changes here in these particles coherently with the magnetic field. Next. Let's take a look at the high energy particles. In this upper scale now from the Stone experiment, cosmic rays, they're increasing. Again, they're showing this step relationship. And again, these are the low energy particles repeated, showing the stepping functions. Well, what's going on? What we're losing are all these energetic particles here. These low energy particles are particles that are actually accelerated someplace within the heliosphere, either by the sun or by the interaction of the solar wind with the planets or the planetary radiation belts themselves, or thought to be associated with a termination shock process. Still under study as to what the sorts of all of them are. But in any event, this is where we're going to concentrate on, is this period in the middle of the year 2012. Next slide. This now shows the magnetometer data, magnetic field magnitude, again, tenths of nanotesla. This is now the longitude of the magnetic field, and this is the elevation angle, and again, the cosmic ray particles down at the bottom just to keep you oriented. This with the termination shock, the magnetic field actually increases in the heliosheath and fluctuates back and forth in magnitude quite irregularly, but the longitude angle is characteristically around 90 or 270. Well, this is the Parker-Archimedean spiral angle, 90 or 270, depending upon whether the magnetic field is coming from the northern hemisphere of the sun or the southern hemisphere of the sun. There is in the heliosphere the structure we call the sector structure, which tells you which polarity you're working with, where the magnetic field comes from to its solar origin. Again, the cosmic rays increase, and when we get out here, they seem to reach a very high level. I believe it's my last slide. I promised to do this in 15 minutes. That's why I'm rushing. And here we are, again, with a magnetic field magnitude, longitude, latitude, cosmic rays. And what we see here on a somewhat expanded time scale, as I said, in the middle of the year 2012, here's a sector boundary. Sector boundary 2, we've identified this one, sector boundary 1. Here's a complex sector crossing, CS0, where the magnetic field actually gets to be its strongest. Then it falls down, and then it comes back up. In this region, Don Gurnet's experiment had, prior to our confidence in our interpretation, identified waves that it could interpret only in the framework of the interstellar plasma densities. The last slide. EPO, energetic particle oscillations. That's what Don Gurnet's instrument was showing prior to our final processing of our data. It takes a while for us to process the data. People expect, and I must say the press has had a lot of fun about a year ago with the question, where is Voyager 1? Because there was some dispute about where is Voyager 1. Is it outside or inside? Well, I can tell you with confidence we know where it was, but we can't always tell where it is in a sense unless we can see where it's been and what it's going into. This is the last slide I'm showing. This is the first published measurements of the draped interstellar magnetic field. These results are also being published in the AJ Astrophysical Journal and presented at a conference on astrophysics being held down in South Carolina this past week. The orientation is not quite at 270. That difference is important. That's why it's a draped interstellar magnetic field over the heliosphere, over the heliopause. So we think this is where the heliopause is to be identified in this region, the CSO, the complex sector observation boundary, and this is its latitude. The direction of the interstellar magnetic field is estimated by astrophysicists as well as the magnitude. They can't estimate it locally because it's always an integral average of properties that they derive by observing these, shall we say, the sparkling stars light for the polarization. The magnitudes which they have estimated are that the interstellar magnetic field generally is thought to be between 0.3 to 0.5 nanotesla. We're showing that locally the magnetic field, interstellar field, decreases somewhat after passing the heliopause, but then increases. And this shock is that bow shock that was shown in the previous diagram for the outermost boundary. We've already published, we knew that this was a pressure wave shock. We could identify that with our data at that time. So we've been measuring and been in interstellar space now for over a year and a half. And I thank you very much for listening.